Okay, so moving into the next unit here, which is about probabilistic modeling, which is something we'll need for input modeling. We'll talk about statistics after the midterm, probability before the midterm. So then next week, that's when we're going to start with ARENA. So you'll start using that lab textbook. So there is access options for that lab textbook for a number of different versions available on Canvas under the kind of the course textbook information. So most of the lab exercises will start with a kind of a scaffold built on an exercise which is in the book, which has some context and things, and then we might then modify those things in different directions. So in order to sort of know where to start, you need that access to that textbook. So that will be something we'll start with next week. Homework B1 solutions are available on Canvas. There's that new homework C, which is available, that the homework D for this unit will be available on by Thursday, if not before then. So, and then those will be the last homework assignments before the midterm. So there's these Canvas activities, just also as a continuous reminder for homework C2, this will be due on Tuesday, the day of the next lecture. So technically we don't cover random number generation until unit E, which is right after this probabilistic unit. But in order for me to make sure you get practice on both the random number generation and the random variate generation, two things we need in the midterm, then we kind of compressed homework C2, and that's primarily because the random number generation is such a formulaic plug and chug thing, and it tell you kind of exactly where to look in the book to sort of plug that in. And when we get to Unit E, we'll talk more about the background and we'll motivate where those formulas come from and so on. But the actual practice of generating those numbers that you do in that homework is, I think, relatively straightforward. So this is the one example where on that homework, you won't see it in class before you do it in the homework, but it's I think, pretty mild. So just something to look out for there. And like I said, that allows for the random variate generation, which is different than random number generation, for us to do that before the midterm, so that on the midterm we can test you on both random variate generation and random number generation, which is a nice kind of conceptual grouping, so that then after the midterm we can focus more on running the sims and doing inferential statistics on those sims. So we're much more kind of modeling pre-midterm and statistics post-midterm. It's kind of the idea here. Couple of clarifications. If you've not seen this notation before, sometimes this question comes up. If I were to say A mod B, what I mean by that is the remainder when you divide A by B. So 5 mod 3 would give me 2, because 5 divided by 3 has a remainder of 2. So that's just sort of a formal way to say remainder modulus. So if you see that, that's what that is. And then also on this homework, make sure to show your work for the grader. So in question 1, that might mean including formulas, showing your calculations for each step. So in that case, you're going to be generating numbers sort of step by step. And so in this case, it was sort of the idea of making sure you kind of show, well, how did I take numbers from the previous step and plug them into the next step, so that it doesn't just give you a string of numbers. And then in question 2, when you do that kind of test to see if those numbers, the type of randomness that comes out of those numbers, if you summarize your results in a table, then make sure you indicate the formulas that, like in every row, like this row's formula is this row's formula is this, and so on. And that's actually very similar to what the book does. So follow the book's example, where you don't necessarily have to show me every single calculation for every single cell, but you can sort of tell me that this row's formula, this row's formula, this row's formula, so I know how you generated those cells before you do that stats. So that's kind of homework C2. Homework D2 will be available very soon. I just have to update the random variate problem for this year. So it'll be available by Tuesday. This is 2 questions related to random variate generation. So we'll learn the difference between random number generation and random variate generation shortly. Like I said, there's the Canvas activity. And then I keep talking about the midterm. It's about 2.5 weeks away. So basically we're going to wrap up, unit D, that's this week. And then E will be the bottom half of next week and the first half of the next week. And then we've got a midterm, basically lecture F. So unit F is just a midterm review. Unit F is sort of the midterm. So there will be a midterm review we'll have in class. And then the next week, we'll actually have the 2 stages of the midterm. So Tuesday will be that individual stage that you do on your own. You can come to class. I will be here at this time slot in class. If you want to bring a computer and do it in class, that's fine because it's a Canvas-based. But you'll also have all day that you could do it. Whenever you start it, you'll get 90 minutes. And so you can't stay in here for 90 minutes if you come here. You only have the 75. I just give you 15 extra for technical challenges at home or elsewhere, wherever you want to do it. And so if that day, if you would like to do it some other time during that day, that's totally fine. You don't have to come into class, and you just, but whenever you start it, make sure you end it within that 90-minute window. And then stage 2 will be Thursday of that week, which will be that group exam where it's the exact same exam, also on Canvas, no time limits. They're just, you have to get it done in the availability period, and you can work with anyone else enrolled in the course this semester, and you can work. You can use your words. You get I think I've got 2 pages front and back. I'd have to double check that for sure, but I'm pretty sure I intended for 2 pages front and back of notes that you can use in stage 1. Stage 2, you can use all of your Canvas notes, all of your personal notes, the textbook, and so on. Again, it's the exact same exam. And 80% of your score comes from your individual, 20% comes from the group and the open book. So that gives you an opportunity to sort of maybe correct things and revise things. And then that also really helps me because a lot of times I'll see things that will get corrected across the board on stage 2, but then a couple of things that happen to just make their way through that didn't quite get fully corrected on stage 2. And then that sort of shows me where the problem areas are, where the continued difficulties are. And so that's part of the reason I do that. So that's kind of the plan there. Like I said, the lecture F will be a midterm review. So that I've stripped out kind of the key slides from all of the previous lectures and if there are no questions, then I'll just kind of bring those up as a reminder and to see if those generate questions. But if there's questions, then, we can just totally spend the whole period answering questions. We can work problems, and so on and so forth. And so that's an option there. That midterm's over these chapters of the Banks book, which is basically the units A through E, and the big focus is on sort of these lectures A1 through F, labs 1 through 3 and 5. So I'm not planning on talking about really net logo. I might bring up agent-based modeling in one question, but that's kind of it. And then your homeworks B1, C2, and D2 are sort of that. Those are kind of really good. If you can ace these homeworks, then you'll be really well suited for that midterm. So that's just summarizing here. Stage 1, individual closed book notes, 2, two-sided hand-produced sheets. So by hand-produced, I mean, I just don't want you taking screen caps of things and just putting them in. I want you to either type them or write them, not just copy and paste things into the sheet. And then stage 2, collaborative and open notes. So that's all of that. Any questions about this lineup here? There are, I think, in the midterm unit, you can find, I've put a bunch of other resources as well, sample midterms, et cetera, so you can kind of see what that looks like. So if you have any questions of that, or if you have trouble accessing those resources, let me know. And again, the Rockwell competition, I'll keep putting this up until after, September goes here. And so if you're interested, register by the end of September. Same thing with FlexSim. And I don't know the deadlines for the Simio, but that could be something looked into there. So any questions? Great. Okay. So wait for one of those. So motivation for why we're talking about probability today. and probabilistic models on Tuesday. So I've talked about this problem before. We've got variation in real systems, customers, passengers, whatever, they arrive. There's all of this sort of variable spacing in them, for example. And so rather than trying to figure out what are all of the real details that determine why one person's, why one gap here is smaller than another gap here, then what we do is we take the data that is likely complex and has some causal structure, and we just build a phenomenological model. So that means we just take statistical data from the real world and we say, hey, that looks like that always sort of fits consistently a particular distributional curve. So I don't actually care what the causal factors are that went into building that curve. As long as I can draw random numbers from that same curve, then I can generate variation at the kind of right interface with my simulation model. And that's all I need. I just need people to be arriving to my sim in a consistent way with reality, even if the causal factors don't necessarily line up. So in reality, there's a deterministic process that determines a variation. In our sim, it's like it's quantum mechanics. It's all randomly generated. And so then our question then is, how do we build those probabilistic models? So that's kind of the idea here. That's so-called a stochastic approach. It makes a guess or a conjecture. So stochastic is not another word for random. Stochastic is a philosophical modeling approach where you use randomness because you don't care about the real causal factors behind the system, but the randomness makes it easier for you to model the system. So saying, I don't know where this variation is coming from, so I'm going to make a guess or a conjecture. So stochastic comes from the Greek for guess or conjecture, that my system my system's variation just comes from some random process, again, like quantum mechanics. It's just there's some sort of entity that is rolling dice that is determining these outputs, and the outputs come from the dice. And I'm not saying that that's actually what really happens, but I'm saying that if I can weight the dice correctly, then you're not going to be able to tell the difference between the outcomes I get from the dice rolls and the outcomes I get from reality. That's what we mean by stochastic modeling. So input modeling is further to saying, okay, now that you've taken that stochastic approach, what models are you going to use to generate these variations? So now, rather than doing the deterministic process of saying exactly what are all the details for why this family arrives at a different time than this family and so on and so forth, now you focus on distributions and say, okay, what is the right distribution? What distributions are out there and what are the best fit for the real data that I can see? And that is input modeling. So it selects the probabilistic models that mimic our realistic system. So another view for this, if you don't like this sort of philosophical perspective, is that uncertainty itself is a source of noise. And so I can never be certain about where this variation comes from in the real system. And that if I leave out those deterministic factors that go into this, I basically have a huge residual term, a noise residue that sits on top of my model. And the stochasticity here is just making sure we've got kind of the right noise residue. So either you buy what I'm saying and that you say stochasticity is just a modeling approach where I replace determinism with a simpler or fewer parameter random model, or I say I purposely leave stuff out of my model and that creates a gap between my model and reality, and I fill in the gap with randomness to better model the uncertainty that I've added to my system by leaving stuff out. Those are kind of two approaches to look at it. We end up in the same place though. How do we figure out what these models are? And that's why we need to know a little bit about probability, because you can't wrap your head around randomness without having a mathematical framework for it. And that's where probability comes from. Probability theory is built, and by any questions on this approach is, basically motivated by all the things we've been talking about so far, Gesundheit. Hopefully in some of the hand simulations, you're starting to feel this basic idea as we kind of get up these input models that are generated randomly. All right, so probability theory is a branch of something called measure theory. So it's a much more general mathematical construct. So at one time in, say, the 1900s or so, and maybe a little before that, people started realizing that they needed a mathematical framework that would formalize how you deal with weighing things. So, if you have objects like this, they have conserved mass. If you cut a piece of it up and you weigh that piece, and you do that for a bunch of different pieces, and you put all the pieces together and you weigh the whole thing, then theoretically all those weights should add up to the weight of the whole. And so people realized that if you just thought generically about sets in mathematics, that wouldn't always happen. So there are ways in which you can say the set of all real numbers between 1 and 6. There are ways in which you can slice up mutually exclusive parts of that set and then weigh them, ask how many numbers are in there, and then add them all back up together. And the sum will be different than the weight of the whole. And people realize that could be a problem if we start using these mathematical formalisms to describe real entities, which we want to have these additivity properties. And that's where measure theory came in, as it said, if we do have these sets, how do we map parts of sets to weights on the real line? And once, so this sort of came by thinking about these massive objects, but then people realize this also perfectly fit what we need for thinking about randomness and probability. Because ideally, likewise, if you said there's 100% probability that something's going to happen, and somebody says, well, which something? You could say, well, there's a 25% probability that this subset will happen, and a 40% probability this other, and so on and so forth. You start realizing that there's a conservation approach there as well, that you want to make sure that if you're taking probabilities of subsets, that all of those probabilities, if you add up all of the things that could possibly happen as the whole, should add up to 100%. The people realize that the same problems that they were trying to solve by coming up with mathematical formalisms to deal with mass also applied to deal with probability. And that's the reason why you hear these terms like probability mass function, probability density function. These terms, mass and density, are not accidental. They're not coincidental. They come from a conceptual framework that thought about real physical objects and was just mapping the probability thinking onto that, or mapping the mass thinking onto probability. So that's the type of thinking that I want you to have when you look at distributions, is that think about, where is the mean in this distribution? Well, if I were to grab an object here, like this bucket, and I were to show you this bucket here, and I were to ask you, if I wanted to put my finger somewhere underneath this bucket to figure out where it would balance, you probably wouldn't tell me to put my finger here. You probably wouldn't tell me to put my finger here. You probably would tell me to put it like right here in the middle, and then it hopefully would balance or be close to balance if I got it, close enough. And that, I think, is a very natural process for you to look at this and figure out roughly, now if I tilt it this way, where do I need to put it? Well, now that it's got this kind of thicker lip here, maybe I need to shift my finger over a little bit to deal with that, and maybe it won't be perfectly in the middle. That reasoning is exactly the same reasoning that when I show you a distribution, you should figure out where is the mean of that distribution. You shouldn't need to calculate it. If I just show you the shape of a distribution, the point along the x-axis that balances that shape is the mean. And that comes from the idea of center of mass. The center of mass of a physical object is the same thing as the mean of a probability distribution. And that's because they come all from the same mass. So that's the type of thinking that I want us to get into as we start looking at distributions, to gain intuition into them. So to get there, we need to define a couple of things. So random variable. So this is a complex term because unfortunately a random variable is neither random nor variable. It's a function. It's a deterministic function between sets and outcomes. So a random variable maps a space of possible outcomes of an experiment to a so-called measurable space. And so for this class, the only measurable space we worry about are the real numbers. And so the idea here is that every outcome might map to a particular real number, and every set of outcomes maps to a set of real numbers. And that mapping is the so-called random variable. So when people talk about random variables, that's what they mean. It just organizes outcomes in the real world numerically so that their uncertainty can be mathematically modeled. So for example, the number of coins landing heads up is a random variable. If I flip 10 coins, then I could say that outcome, I just see a bunch of coins. How am I going to quantify that outcome? Well, I'm going to count all of the heads, and then that number of heads, that is the number that I'm going to actually then put into my mathematical model. I could have chosen a different way. I could have counted the number of tails, and then that would be the thing that maps to my mathematical model. So a random variable is often written as a function here. So it's interesting that the projector has, yeah, it's interesting that I got dropped there. So there's a font issue here. So this should be an omega. So I'm not sure why that dropped out, but I'll make sure these slides are fixed so that are uploaded here. But this isn't going to matter too much because I'm not going to quiz you so much. There's shorthand that we're going to end up using. But imagine that this is some set. This is a capital omega outcome space. And so this random variable maps all of these outcomes to the real line. So maps outcomes in here to the reals. We call the outcome space, the thing that goes here, the sample space. And so the sample space here will include all of the mutually exclusive outcomes from an experiment. So every point is something that can't happen. Like there can only be 10, if we think about like, all of the different ways that 10 coins can land, there's only one, like there's two to the number of coin different outcomes that could happen there, and each one of them is mutually exclusive. So each one of those physical reality outcomes that can happen, each one of the ways the coins can fall, is a single point in our sample space. And we're going to map each one of those into numbers. That's what the random variable does. So the range of our random number is the set of the real line that corresponds to all of the things that were mapped from the physical world. So this one, for coins, that's pretty easy because you just count them. So if there are 50 coins, then the number of coins landing up heads, well, that could be anywhere from 0 to 50. So the range of that random number would be all of the whole numbers or all of the natural numbers from 0 to 50. And that would be what we mean by the range of a random variable. So for convenience, we'll often drop this function notation and just call the random number x. And so, or the random variable x. So it looks like a variable, but remember, it's not actually a variable. We're never going to say x equals 2. We're never going to assign anything to it. X just represents the sort of numerical perspective that we have decided on outcomes from the physical world. That's what a random variable is. An event, so again, this is supposed to be omega here. So this is our sample space, and this is our sample space. The term event is a subset of the sample space. It is a set of outcomes. So we can say there could be a single event, like an event could have a single outcome in it. Like we could say the event that we have a certain set of coins that came up heads. That could be an event. Now, there may be a bunch of different ways for coins for there to be 36. Like if I have 50 coins, there are a bunch of different ways that 36 of them can come up heads. These 36 can come up heads, these 36 can come up heads, these 36 can come up heads, and so on and so forth. So, if we could say the event is any way that 36 coins comes up heads, that would be our event. So it's a subset of outcomes. So each individual way that 36 coins came up heads is an outcome. All of those different ways together is an event. So that's the reason why we have this notion of event, is that there's often multiplicity in our we don't care about every individual outcome. We care about outcomes that have a common property, like 36 coins are coming up heads. So I give an example, single outcomes here. A six-sided die shows 4 dots. But I could say, other events is that like a six-sided die shows at least 4 dots. So there are multiple ways that you could show at least 4 dots on a single die, or in a single dice, a single die. And so that And that's kind of an example what we mean by the difference between events. You can have outcomes, but then you can have events, which are sets of outcomes that may only include one outcome or they include multiple outcomes. So that's the difference between an outcome and an event. It is the events that we will assign probability to. Okay, so are there questions about, and again, I'm sorry that the capital Omega isn't showing up here. So again, I'll see why that font isn't, or why that character isn't rendering. But are there questions about this distinction between outcomes and events? Okay, so as I mentioned, the scale that we use, because probability is all about mass, the scale that we use to weigh events is the probability measure, which we use the notation capital P lowercase r, usually this way, probability. And you say that it's a scale that can weigh each event. So this would be kind of the function here. So that's what we mean by the probability of an event is sort of the, again, the weight of an event. And what do we mean by weight? And for now, we can think of it as sort of the frequency of, how often that event can occur or will occur. And so we choose distributions to try to map from these numerical spaces to this frequency distribution that we get in real life. And so that's kind of what probability is there for. It's meant to capture and characterize the how often things occur in reality in a mathematical way. So that's what we mean by a probability measure. And it ensures conservation of mass. And so it may seem weird, but if you just arbitrarily define probability measures without a couple of other mathematical assumptions, then there are pathological ways for you to define a probability measure or a set of outcomes, or a set of, well, certainly a set of outcomes is kind of the problem, or the measure space. There are different sort of ways that you can create. You can say, well, I'm going to map outcomes to this weird subset of or this weird special set that isn't all the reals, it's something else. Like there's different ways you can make these choices that make it so you don't have conservation of probability anymore. So that if you could say, well, if I have an uncountable number of things that could happen, like a real number, like something that maps to the real line, there are ways in which you can take those subsets out and weigh them and ask what's the probability of each subset, and then sum them all together so that your probabilities add up to more than 100%. And things like using the things that we do in this class are automatically going to fit the assumptions that measure theory has figured out that will prevent that from happening. But if you go into more advanced courses in probability modeling and measure theory, then you'll actually start trickling into, when you start trying to build probabilistic models for more complex systems than we talk about in this class, you actually do start worrying about the formalisms and choosing the wrong formalism, because if you choose the wrong formalism, you might lose conservation of mass, which is really important for probability to work. And measure theory has defined all the things that need to happen to guarantee you're going to get conservation of mass. So it's a little bit heady of a topic. I'm not going to quiz you over all of these sorts of details, but you're at a 400 level class in engineering. You should know where these things come from. Probability comes from measure theory. Measure theory largely comes from math that makes sure that you conserve probability or conservation of mass or conservation of probability. So we weigh all these things. And so because they're weights, then there's certain things that should be true about them. So as I said, event weights are the sum of the constituent outcome weights. The weight or mass of the entire set of things that could happen, we're just going to normalize and say is 1. And that's like the weight of the universe is 1. And the weight of any individual event is non-negative. It can be 0, but it can never be negative. All right, so any questions about probability measures, these sort of constraints here? Okay, so we now can say what types of random variables do we have? And we deal with discrete random variables And so this should start feeling more like review from 380 and 385, but we deal with discrete random variables and continuous random variables. So what is a discrete random variable inside this formalism? A discrete random variable is one in which has a range that is finite or countably infinite. So this discrete is maybe in a very loose way related to the discrete that we talk about in discrete event system simulations, but that discrete is about time being countable, not about the values that you can get at any instant of time. This is a sort of about the values that you can get. So it's like the number of people in this classroom, that is a discrete random variable that could be modeled in a discrete event system simulation, but also the amount of water in a glass or the temperature in a room, as we'll find out, those are continuous random variables, and both of those could show up in a discrete event system simulation. It just means that their values come from a smooth scale instead of a graded scale that has these little stops on it. And that's all discrete means, is it has these little stops, these little countable stops. It can be infinite. So just because something's infinite doesn't mean it's not discrete. It just means that if it is infinite, you can assign every outcome to an integer and you'll get a one-to-one mapping. And so that's what it means to be countable. So a range of our random variables, we'll often write them as R sub X. And in the case of a discrete random variable, it will just be a set with commas there. So we don't specify any ranges necessarily. And then for each element, we might use this shorthand. So just with discrete random variables, we'll use lowercase p to represent the probability of an individual outcome. We would never do this with continuous random variables for a reason we'll see in a second, because the equivalent for this for the continuous random variables would always be 0. So that's one of the interesting things about continuous random variables, is the probability of any particular outcome is 0. But for discrete random variables, you actually do have non-zero probability for discrete outcomes. And so we use lowercase p followed by an outcome to mean the probability that the random variable is equal to that outcome. So this is sort of mathematically, but very often we'll just use this notation here. Those probabilities all have to be non-negative, and they all have to sum up to 1. So this little p, we're going to call the probability mass function, or PMF. And the graph that combines the outcomes with the probability mass function, we call the discrete probability distribution. So you could plot the probability distribution, and it's just a plot of the probability mass function. So X is the number of jobs arriving 1 week at a job shop. So in principle, you could have an infinite number of jobs arriving in a week if you had a very fast arrival rate. But we still view it as a discrete random variable because it's countable. So the range of X are all of the non-negative integers. So all of the natural numbers from 0 to infinity is the range of this random variable. So there potentially would be a probability assigned to all of these numbers all the way up to an unbounded set. So all the way up to infinity. So that's what I mean by discrete random variables. So any questions about these definitions? So if we were to look at a distribution here, then this is, the number of spots face up of a die after a toss, and this might be an unfair die, so that some faces come up more frequently than others. So we've got 6 possible outcomes. So this is a discrete random variable, which face comes up, and we labeled the faces, so that's our random variable, by how many dots were on each face. So 1 dot through 6 dots. And we, in this particular case, the face with 6 dots happens to be 6 times as likely as the face with 1 dot. So we might say that the probability is proportional to the number of dots on the face, and that gives us the numerators here. But then, where does the denominator come from? Why are all of these over 21? So why is this not just 1, 2, 3, 4, 5, 6? That would also make it so that the probability of getting 6 is 6 times as much as the probability of getting 1. Why are they all over 21? Why are the probabilities all divided by 21 in this case? Yeah. Yeah, so 1 plus 2 plus 3 plus 4 plus 5 plus 6 is all 21. So why do we divide them all by 21? What is a rule of probability measures? What has to happen to the sums of your probabilities? They all have to sum to one, right? So that's what we're sort of saying here is that all of these probabilities not only have to be non-negative, they all have to be 0 or higher, but if you add up all of the possible outcomes, and in this case, the only things that can happen is you get 1, 2, 3, 4, 5, or 6. So if you add them all up together, they have to add to 1. So this 21 just ensures that if you add up all these probabilities, they sum to 1. So a lot of times we'd actually we'll specify things in terms of how they relate to each other, like this thing is proportional to this other thing, because we know that the the normalization factor we can sort of figure out later. So when we're talking about modeling, that's often the case. Is we're more interested in odds ratios, for example, likelihoods, things like that. If you take a more advanced statistics course, you'll learn about Bayesian statistics and ways in which you estimate prior probability distributions, and you find that a lot of those methods get their computational speed by forgetting about this normalization factor, because it's really just put it in there to make sure everything adds up to 1. But when we actually then give someone a probability distribution, in order to make it a real probability distribution, we have to sort of figure out how to normalize each outcome. And so that ends up being an important thing, but kind of the salient feature here is the numerator. The denominator doesn't matter that much, but we eventually have to put it in because we have to make sure they all add up to 1. That's where the 21 comes from. And if I were to plot that graphically, it would look like this. So this would be our, probability distribution function, or probability distribution, which is a plot of this probability density function. Now notice, and I'm going to do this throughout the rest of the class, when I plot probability mass functions, I am going to use these funny little, like they look kind of like pinheads, like, so that they've got a little dot on it and then this vertical line coming down. These are what are technically called Dirac delta measures. These are ways in which, when we plot probability functions, we can concentrate mass onto a point. And so in probability mass functions, you actually can have individual points that have probability. But as we're about to talk about in probability density functions or continuous random variables, you can't have this. And so that will be a key, that that if you have a probability mass function, we're actually saying there's a bunch of mass that's sitting on that point, and that's what that's what this indicates, this little vertical line with the dot up top there. It's like I've taken a chunk of mass and I've set it on an individual point, and that's why they're plotted that way. And again, they're called delta measures, and that's traditionally plotted in this way. So we try never, when we're plotting probability mass functions, to connect the dots. So if I give you a probability mass function on a homework or something like that, and you're plotting it out, don't interpolate. Don't just say, I'm going to plot this thing and I'll get a straight line here, because that implies that there is some mass in between the numbers. So it's really important when you're talking about a discrete random variable to say that all the mass is clumped in 6 places, and we have to sort of plot them like this. So if you don't want to do the vertical bars, that's okay. At least just give me the dots, but don't connect the dots. Really important, probability mass functions, never connect the dots. That said, I probably have some examples that I'm going to show on Tuesday where I may have grabbed probability density functions off Wikipedia, and somebody was maybe not as careful and they might have connected the dots. So I'm not saying it doesn't happen, but formally speaking, at this point, as we're learning how to do this stuff, then we want to practice doing it right. And so don't connect the dots when you plot probability mass functions. Pinheads, that's what we want. All right, questions about discrete random variables? Okay. All right, so continuous random variables. So This is, again, we want to relate to mass. So this is a continuous object. It has density, it has weight all throughout it. If I were to slice an infinitesimal slice of this table, infinitesimally thin, so basically vanishingly thin, if I were to take that salami slice out of there and weigh it, it would weigh 0. But it still has density at that point. So density is like, as I add those slices up together, how does the mass of the grouping that I'm building up change? That's what we mean by density. It's the same thing with probability density, is that I can plot a probability density function. So this is a continuous random variable x, which just means it takes its numerical side, takes all outcomes between A and B, all of them in the real line. Every single real number between A and B is given some probability density. So the whole interval has weight. This table has weight. A subset of this table has weight. I can pick that up and I can say this small portion of the table, this 3-inch wide bar of the table weighs a few pounds. That's what this integral is saying here. But the density at every point, while that has a number, the weight of an individual point is always 0. So the probability of any particular outcome is 0, but the weight of a group of outcomes, of an interval of outcomes, is usually non-zero if you've got non-zero density. And that is exactly what's going on with the weight here. So we'll see that kind of more and more here, but that's what when we plot probability densities. The reason I'm pointing this out, and this is what's going to be emphasized here on the next couple of slides, is that probability density is not probability. Just like density, mass density, linear density of the mass of this table is not mass. So probability density can be greater than 1. It can't be negative, but it can be greater than 1. It is not a probability. If somebody says that, this outcome has a probability density of 16, that doesn't mean it has a probability of 16. That just means that if you were to add a little bit of it in, you would sort of be scaling 16 by the tiny little bit that you're adding, so that the rectangle you would get out of that, height times width, that would be less than 1. So this is the contribution that a very, very tiny rectangle, when you take the rectangle's width times that density, that's the contribution it adds to the probability. But the height of that rectangle does not have to be less than 1. So that's a big thing that when you're first learning this stuff, that's confusing. Probability density is not probability. It can be nearly infinite, because it can, like the mass, I could have a spoonful of something that is the density of the sun. The sun is a very, very dense object. And you could put a very, very tiny amount of it here on the table, and that would make the mass of the table total very, much, much higher. And the density at that particular point, where that little spoonful of sun that I put there would be gigantic, and that density would be a bigger number than the mass of the table. But they're different units. Density is in mass per unit length, mass per meter. This could be grams per meter. That would be my density of this table. If it's a homogeneous density, and then I could say this table contributes 3 grams per meter. So every time I go another meter, I add another 3 grams. That doesn't mean the table is 3 grams. That doesn't tell me anything about the weight of the table. That just tells me that for every little bit of table I add, if I scale that by how wide it is, that's how much I'm adding to it. Unfortunately, because mathematicians don't think in terms of units like we engineers do, they didn't give a different unit to probability density. So both probability and probability density are unitless, which is up, and that's because, again, to a mathematician, X doesn't have a unit. And so that's where a big source of the confusion is. When we take a mechanics class, the mechanical engineers know to put units on everything. So we've got meters here, we've got kilograms here, And so when you see kilograms per meter, you know that's different than kilograms. That's what you should be thinking in your head, is that F here is not probability, it's probability per whatever this unit is, like probability per meter. That's what we mean by probability density. But unfortunately, because mathematicians don't think in terms of concrete things in the real world, then conventionally, we don't have a unit for probability density. But you should think of it as a completely different unit. It's a different quantity. It does not have to be less than one because of that. Any questions about that? All right, let's see that written out a little bit more here. So if this is the probability of an interval, so this is the weight of an interval, which is just the integral of its density from the one side of the interval to the other, then the rules of this is that the probability density, it must be non-negative, just like probability. And if an outcome is not in the range of the random variable, it must be zero, just kind of like probability mass functions implied as well. The integral of the density over the range must be equal to one. That's the only kind of equals one constraint we have. The integral, the sum under the curve, that has to be equal to one. But the density itself can be greater than one. That's what I've been trying to say, is that F has different units than probability. Water's density can be numerically greater than the weight of a cup of it. So just because they have different units, you can't compare one to the other. Because of all of this stuff, then you can ask, if I have a probability density function, what is the probability of a particular point? Well, that's the integral of density from A to A, from that single point to itself. And we know that for most functions that we know how to integrate under, that if you integrate a function from one point to itself, it doesn't matter what the function is, the value is always going to be equal to zero, because it doesn't matter how high the density is. If you're adding no part of it, if it's infinitesimally small, then we're not going to scale that density by anything. So we get zero out. So if you throw a dart at a dartboard, the probability of hitting any particular point on that dartboard is zero. But the probability of hitting the bullseye is non-zero, because that is a set of those outcomes. I can integrate over the density. So I can figure out there's a uniform density of where the darts hit on the dartboard. And if I take that, then the area of the bullseye relative to the area of the dartboard tells me the probability of me hitting the bullseye. But if I say, what's the probability of me hitting a particular point inside the bullseye, that is always zero. Okay. Questions about that? It's a weird concept, continuous random variables, but it's no weirder than thinking about continuous densities in physical mass. So again, probability is just mass. Anything you know about that, you know about that. Okay, so this is just me kind of drawing out all of these things. So the probability at a particular point is zero because the width is zero. So this rectangle is not, it's got a zero width, so it must have a zero mass. This shape is actually got contributes a significant chunk. This is a chunk of the table, so it does have mass. So there's density everywhere, there's only mass here. Okay. Questions about that? So here's an example of something we might model. X is a lifetime of device that inspects cracks in an aircraft wing. So if we're simulating the process of inspecting an aircraft, one of the input models we have to deal with is how often until the thing that we're using, the resource, dies. And so we might model that resource lifetime as this X random variable here, which we might say our input model is an exponential random variable with a mean of 2 years. So here we're saying that it could die at any time, but it also could live forever. And so the range of this random variable is the entire half line of the reals, the entire interval, including zero, from zero to positive infinity. And so we might model that again with an exponential random variable. And if by saying we model an exponential random variable, we're saying that the density in the time outcomes takes on this shape, which is plotted to look like this. So if we were to take this and plot it out, this would be the probability density. So then if we want to know what's the probability that it will die between 3 and 4 years out from when it's, it started being used, then we would integrate under this curve from between 3 and 4. If you said, what is the probability that it's going to die in at exactly year 3, that's 0. There's nothing useful we can say about that. But if you say, what's the probability of it dying between in the first month of year 3, well, we can give you a small probability in this case. And then so the more you ask for, what's the probability of it dying? Well, that's 100%. That's the integral underneath the whole curve. And this has been normalized. That's why there's a 1/2 out front here. So the integral underneath this whole curve is equal to 1. So that's what we mean there. So questions about that example? Okay. So yeah, so this mean here, I already kind of hinted at where does mean come from? Because I said it has a mean of 2 years. So we'll get to that in a second. All right, so a couple of other details that we need to make sure we're all talking the same about. Cumulative distribution function. Cumulative is the key word here, or CDF. This applies identically to both discrete and continuous random variables. We use a capital F for the cumulative distribution function typically, unless it says otherwise. If there are multiple random variables, it'll be capital F sub that random variable, F sub X, F sub Y, and so on. And it is just the probability that the random variable is less than whatever that argument is there. So I would say capital F6. Well, that would mean that is the probability that you're going to get an outcome that is 6 or less. So that's what we mean by cumulative distribution. So for discrete, you add up all of the outcomes that are less than whatever this argument is. And for continuous, you take the integral of your density function from -infinity up to that argument. That's our cumulative distribution function. It seems like kind of a hassle. Why do we have cumulative distribution functions? But it turns out a lot of the things we do in sim, in mathematical analysis, and so on, it's much, much more convenient to use cumulative distribution functions than density functions or mass functions. And that's the reason why we have CDFs. It ends up being, it's harder to maybe think about, but it's easier to do work with CDFs, which is why we'll see them. They have a bunch of cool properties which relate to what I'm talking about here. So for one, capital F is a non-decreasing function. So if A is less than B, then F of A is always less or equal to F of B. The limit of them is always equal to 1. Can anybody see if anybody's paying attention? Why is this the case? Why is the limit of a cumulative distribution function as x goes to infinity always equal to 1? A second to think about that. What do we know about probability? Where 1 comes up there a lot as well. And, what does this definition say? So the f of infinity, so the limit of f as x goes to infinity, is the probability that x is less or equal to infinity. So why would the probability that a random variable is less or equal to infinity always be 1? That's what I'm looking for. Yes, every outcome in a random variable is less or equal to infinity. So this x in the cumulative distribution function is a cutoff where you're saying, I only care about outcomes up to x. And so if you let x go to infinity, you're saying, what's the probability that I get any outcome? And that is the reason why all CDFs end in 1. That's also why all CDFs start in 0. So the limit as you go to -infinity, you're excluding all outcomes. So on the left side, so this side of a CDF, you're always at 0. This side of the CDF, you're always at 1. So a lot of CDFs, well, they're all non-decreasing. So sometimes they're S-shaped or whatever, but they're all going to have this kind of upward trend where they're going to be low down here and high up there. And then if you want to know the probability of an outcome between A and B, if you know the density, you can do the integral. But if I give you the CDF, you don't have to do the integral. I might give you the density and the CDF, But if you see the CDF and all you're looking for is the probability that you go between these two numbers, between these two barriers here, you just subtract the cumulative distribution function at the upper level minus the cumulative distribution function at the lower level. And so that is a fun little thing that you can turn calculus into arithmetic because I've already done the calculus for you if I've given you the CDF. And most random variables, you go to Wikipedia and right down the right-hand side, you get the density function and the CDF right there. So if I tell you that a random variable is modeled as a Weibull distribution with these two parameters, then you can just go to Wikipedia, look up what's a Weibull distribution. Oh, there's the CDF. There are the two parameters. If I need to take the integral underneath that funny Weibull density function, because he gave me the CDF, I just need to do this subtraction right here. Because if I know the integral, where this integral starts and where it ends, and I know the Weibull CDF, then I can get the integral underneath there without having to do any calculus. So those are fun properties of the CDF, very useful. Any questions about this? Okay. So this is an example CDF for a discrete random variable. All discrete CDFs will look like stair steps, where the height of the stair step is that pin head that I was talking about that we plot inside the PMF. So I've basically taken the PMFs and added all of those pins together. So this is the short pin head. This was the slightly next one on top of it. This was the next highest on top of it, the next highest on top of it, and so on. And so it looks like this kind of stair step here, where I've filled in so there's open circles down here because at the instant you hit this outcome, you add immediately that mass. And that's what gives you this stair step function here. So that's what a CDF of a discrete random variable looks like these stair steps. And then what we'll learn in lecture E, before we go into the midterm or lecture E2 here, is that if you give me the CDF, I can draw random variables according to the probability mass function. And so basically, because the CDF always goes from 0 to 1, as we'll learn in unit E, if I draw a uniform random number between 0 and 1 and then map it via the CDF to an outcome, then the distribution of these outcomes will be according to the probability mass function. So even though I had a uniform distribution here, I will get a non-uniform distribution here. And that is how we simulate rolling dice in a computer, is by using CDFs like this. That's what we'll learn about in Unit E. Similarly, this is our cumulative distribution function for our continuous random variable. This is a CDF for that same exponential that I showed earlier. It is 0 for all points this way because the exponential density is 0. So it's 0, and then it starts rising asymptotically to 1 because the probability density function falls asymptotically to 0. So that's what that one looks like. And likewise, if you want to draw an exponential random number in Excel, in Arena, whatever, all you need is the ability to draw a uniform random number. As long as in the computer, as we'll talk about, as you'll see in your homework, and then as we'll talk about going into the next unit, that the computer gives you the ability to draw a uniform number between 0 and 1. If I then have the CDF, then I just invert the CDF so that I take that uniform number and then see what outcome it maps to via the CDF. And I will take uniform outcomes and stretch them out to be non-uniform. That's how I draw exponential random numbers on a computer, is I use the CDF, just like if you're playing a card game, and that card game says, roll a dice. Well, the die roll will be uniformly distributed, but the card will say, if it's these outcomes, this is what you do in the board game. If it's these narrower set of outcomes, this is what you do, and so on and so forth. These are the rules for how you go from rolling the dice to actually what you do on the board. On the board, those outcomes are non-uniform, even though the dice roll is uniform. That's what we're going to learn how to do going in, or talking about this in Unit E. All right. So, any questions about these things before we just need to cover moments, which will only take a moment, and then we'll get you out of here. Okay, and so maybe we will do a clicker at this point. And I will do a numeric. And so my question for you here is, for an exponential random variable, which is a continuous random variable that's distributed between 0 and infinity, that has a mean of 5. So an exponential distribution with a mean of 5. We haven't really talked about exactly what that means yet. What is the probability of an outcome of exactly 5? So exponential random variable, it's continuously distributed from 0 to infinity. It has a mean of 5. What is the probability of getting exactly 5 as an outcome in that exponential random variable? Just looking for a number, an exact number. So put your exact number into the clicker. And I'll wait for maybe another 15 seconds. So what's the probability of a particular outcome? What's the probability of 5 when I have an exponential random variable with a mean of 5? All right, go ahead and stop that. All right, so results I got out here, 83% of you chose 0. And then I don't know why I guess these ones were typed in differently here. Oh, right, no, gotcha, the frequency distribution. And then these other numbers, which seem a little random, but 4 and 21, but 0 is what I was looking for. So again, the lesson here is the probability of any individual outcome in a continuous random variable is always 0. That's the weight of an infinitesimal slice of a table. It's always 0. No matter how dense the table is, if it's a 0 width slice, it's 0 weight. Okay, so let's close up here with our definitions here of moments. So the most important moment is the expected value, the mean. So the expected value of a random variable is the center of mass of the distribution. So it is the balance point. If you're to make that distribution, sometimes I'll do that. I have a piece of cardboard in my office that I cut out into like a Weibull distribution or something like that. And if I'm good, I can balance it right where I draw on the mean, on it. And so it's the center of mass of a distribution. So how do you calculate that? Well, if you take a statics course as opposed to a statistics course, then you have to figure out how to calculate centers of mass of beams and things like that. And it's the same math. So I just basically take for every point where there is mass, I multiply it by the distance from the end of that entity. So basically the outcome times its probability. I take all of those, which are the moments that are generated. So that's kind of like the leverage, So I'm taking each one of the outcomes times their mass, and I add them all up together, and then that will give me the expected value or the center of mass of the distribution. So in the die roll example, I take 1 times probability of 1 plus 2 times probability of 2 all the way up to 6 times probability of 6. And so the farther out you are, like 6 is a big number, the more leverage you have. The leverage of an outcome is its influence on the mean. So just like in teeter-totter, if you go way out to the end of the teeter-totter, even if you're lightweight, so lightweight would mean low probability, you have the ability to move that teeter-totter around because you have lots of leverage. So likewise, if you have very, very rare outcomes in a distribution, it may greatly affect the mean of that distribution, but then somebody will say, oh, but that's because there's this outcome that has a high amount of leverage. And that is, again, that mass talk. And that just means that there are certain points that are greatly influencing the mean, and most of the outcomes aren't actually close to there. For a continuous random variable, we get that by taking the kind of analog of that, where f of x dx, that together is like a probability, and then x is like the outcome. So I'm just, instead of integrating under the density function, I integrate under the product of the density and the outcomes. So, that's how we calculate means. And so we will often use the notation mu for mean and sub whatever the random variable is. So if it's a random variable x, mu sub x, we also will call that the first moment of x. Again, if you've taken a statics class and remember any of that, all of this stuff should look like moments, and it is. And so all of that stuff was borrowed and plopped right into probability. So in probability, we have moments because we borrow it from what they did in mechanics and statics. And so the first moment is identical to the mean, which is identical to the expectation. 3 words for the same thing. Questions about that? That meaningful? Okay, so the example here, this is our exponential distribution. And so the mean, if I were to take the integral of x times this, so if I were to plot x times this, it would be a different curve. And if I were to take the integral underneath that curve, it would give me a number. And that number would be mu of x, which in this particular distribution would land me right here. And that is the point that if I were to put a little fulcrum, if I were to cut out this shape, then that little fulcrum would be the thing that would balance. So I've got points out here with a lot of leverage. So even though they don't happen very often, they have very little mass, they're so far out, they balance out all of the points that do happen often. They have high probability that are closer to the fulcrum. And that's where we get the mean. Okay. So then higher moments. So that was the first moment. What about the next higher moment? So we can define any number of moments, any countable moment here. So by the nth moment, so we can have the second moment, the third moment, and so on. It's the same formula, but that little x that you put times the probability, you raise to that. You don't raise the probability to that. You just raise the thing out front. So you just, instead of having outcomes 1, 2, 3, 4, 5, 6, you have outcomes 1, 4, 9, all the way up to 36. But the probabilities stay the same. Same thing with the continuous here. And moments, these higher order moments will make it easier for us to calculate other things of interest to us. And so like variance. So variance is an attempt to capture the spread of a distribution. So you can have 2 distributions that have the same mean. So one distribution puts all their mass at the fulcrum. The other distribution puts half its mass a meter from the fulcrum and half its mass another meter from the fulcrum. Both of those have the same mean, but one of them has a higher variance. It has more options, more variation. And the variance is an attempt to capture that. So the variance of a random variable is the expected value of you create a new random variable, which is your random variable minus its mean. And so that's like it shifts your random variable over so that its fulcrum is at 0. That's all that does right there. And then it takes the square of that random variable. And so that means that, some of those values, because you shifted them, are going to be negative and some are going to be positive. By squaring it, then this new random variable inside or outside the square is going to all be positive. And the mean of that new random variable is a metric of the variance in your original random variable. That's where that comes from. And this look ugly to calculate out, but it conveniently has the property that if you can calculate the second moment, which is easier to calculate, and subtract the square of the mean, you get exactly the same thing. So very often, if you look up a random variable, it will give you a list of all of its moments, like all the formulas for each of its moments, because it knows that properties like variance can be built up from functions of the other moments so that you don't have to do all the ugly calculus yourself. So that's the reason why we have higher order moments, is we can build useful quantities out of them. So variance is just one example. Now variance, the square root of variance, we call the standard deviation, and the symbols that we'll use is that a little sigma will be our standard deviation signal and variance will be sigma squared. Okay. Questions about moments? Okay. I guess I should also maybe mention that I wrote this out, but I didn't say it here. But this variance we refer to as the second central moment. And that's a hint at that when you subtract the mean off, you create a new random variable, and that you're then now taking the second moment of that random variable. So the central moment is a moment of your random variable after you've subtracted off the mean. So the second central moment ends up giving you the variance. So those are terms we'll use: second central moment, variance, square of standard deviation. Those are all the same thing. Okay. All right, well then let's close then with second clicker here. And I'll make this the standard short answer. And so the answer here is give me an alternative word for the word mean. So what is one of the other terms that we use instead of the word mean? And I'll make sure that's running. Yep, okay. And that's all I've got for you. So we'll talk about actual distributions we'll use in input models on Tuesday. And have a good weekend. Well, I mean the I would say in the future, make sure, because I said I gave the countdown. Yeah, I think you'll probably end up getting credit, but if you don't end up getting credit, then let me know, and then I can give you credit for this one. But in the future, you just whenever I close it, that's the last